Superparamagnetism is a form of magnetism which appears in small ferromagnetic or ferrimagnetic nanoparticles. In sufficiently small nanoparticles, magnetization can randomly flip direction under the influence of temperature. The typical time between two flips is called the Néel relaxation time, in the absence of an external magnetic field. When the time used to measure the magnetization of the nanoparticles is much longer than the Néel relaxation time, their magnetization appears to be an average zero. They are said to be in the superparamagnetic state. In this state, an external magnetic field is able to magnetize the nanoparticles, similarly to a paramagnet. However, their magnetic susceptibility is much larger than that of paramagnets. The Néel relaxation in the absence of magnetic field. Normally, any ferromagnetic or ferrimagnetic material undergoes a transition to her paramagnetic state above its Curie temperature. Superparamagnetism is different from this standard transition since it occurs below the Curie temperature of the material. Superparamagnetism occurs in nanoparticles which are single domain, i.e., composed of a single magnetic domain. This is possible when their diameter is below 3 to 50 nanometers, depending on the materials. In this condition, it is considered that the magnetization of the nanoparticles is a single giant magnetic moment, sum of all the individual magnetic moments carried by the atoms of the nanoparticle. Those in the field of superparamagnetism call this macro-spin approximation. Because of the nanoparticle's magnetic anisotropy, the magnetic moment has usually only two stable orientations antiparallel to each other, separated by an energy barrier. The stable orientations define the nanoparticle's so-called easy axis. At finite temperature, there is a finite probability for the magnetization to flip and reverse its direction. The mean time between two flips is called the Néel relaxation time, tau n, display style tau_n, and is given by the following Néel Arrhenius equation: tau n equals tau 0 exp k v k b t. Display style tau_n equals tau_0 exp left frac kv k_b_t right. Closing curly bracket, where tau n display style tau_n is thus the average length of time that it takes for the nanoparticle's magnetization to randomly flip as a result of thermal fluctuations. Tau 0 display style tau_0 is a length of time characteristic of the material, called the attempt time or attempt period. Its reciprocal is called the attempt frequency. Its typical value is 10⁻⁹ to 10⁻⁻10 second. K is the nanoparticle's magnetic anisotropy energy density and V its volume. kV is therefore the energy barrier associated with the magnetization moving from its initial easy axis direction through a hard plane to the other easy axis direction. Kb is the Boltzmann constant. T is the temperature. This length of time can be anywhere from a few nanoseconds to years or much longer. In particular, it can be seen that the Néel relaxation time is an exponential function of the grain volume, which explains why the flipping probability becomes rapidly negligible for bulk materials or large nanoparticles. Blocking temperature. Let us imagine that the magnetization of a single superparamagnetic nanoparticle is measured and let us define tau m display style tau_m as the measurement time. If tau m tau n display style tau_m gg tau_n, the nanoparticle magnetization will flip several times during the measurement. then the measured magnetization will average to 0. If tau m tau n display style tau underscore m ul tau underscore n, the magnetization will not flip during the measurement. So the measured magnetization will be what the instantaneous magnetization was at the beginning of the measurement. In the former case, the nanoparticle will appear to be in the superparamagnetic state, whereas in the latter case it will appear to be blocked in its initial state. The state of the nanoparticle, superparamagnetic or blocked, depends on the measurement time. A transition between superparamagnetism and blocked state occurs when tau m equals tau n display style tau underscore m equals tau underscore n. In several experiments, the measurement time is kept constant but the temperature is varied. So the transition between superparamagnetism and blocked state is seen as a function of the temperature. The temperature for which tau m equals tau n display style tau underscore m equals tau underscore n is called the blocking temperature. T b equals k v k b lane tau m tau 0 display style T underscore b equals frac kv k underscore b lane left frac tau underscore m tau underscore 0 right. Closing curly bracket, closing curly bracket, closing curly bracket. For typical laboratory measurements, the value of the logarithm in the previous equation is in the order of 20 to 25. Effective a magnetic field. When an external magnetic field is applied to an assembly of superparamagnetic nanoparticles, their magnetic moments tend to align along the applied field, leading to a net magnetization. The magnetization curve of the assembly, i.e., the magnetization as a function of the applied field, is a reversible S-shaped increasing function. This function is quite complicated, but for some simple cases, if all the particles are identical, same energy barrier and same magnetic moment, their easy axes are all oriented parallel to the applied field and the temperature is low enough, Tb less than TkV, 10 kilobytes, then the magnetization of the assembly is m h approximately equals n mu than mu 0 h mu k b t display style m h approx n mu than left frac mu underscore 0 h mu k underscore b t right. Closing curly bracket. If all the particles are identical and the temperature is high enough, T kilovolt per kilobyte, then, irrespective of the orientations of the easy axes, m h approximately equals n mu l mu 0 h mu k b t display style m h approx n mu l left frac mu underscore 0 h mu k underscore b t right. Closing curly bracket. In the above equations, n in the density of nanoparticles in the sample, mu 0 display style mu underscore 0 is the magnetic permeability of vacuum. Mu display style mu is the magnetic moment of a nanoparticle. L x equals 1 than x minus 1 x display style L x equals 1 than x minus 1 x is the Langevin function. The initial slope of the m h display style m h closing curly bracket function is the magnetic susceptibility of the sample. Chi display style chi equals n mu 0 mu 2 k b t Display style chi equals frac n mu underscore 0 mu caret 2 k underscore b t. In the first case, chi equals n mu 0 mu 2 3 k b t. Display style chi equals frac n mu underscore 0 mu caret 2 3 k underscore b t. In the second case, the later susceptibility is also valid for all temperatures T greater than T b. Display style T greater than T underscore b. If the easy axes of the nanoparticles are randomly oriented, it can be seen from these equations that large nanoparticles have a larger micro and so a larger susceptibility. This explains why superparamagnetic nanoparticles have a much larger susceptibility than standard paramagnets. They behave exactly as a paramagnet with a huge magnetic moment. Time dependence of the magnetization. There is no time dependence of the magnetization when the nanoparticles are either completely blocked T b display style T alt T underscore b, or completely superparamagnetic T b display style T GGT underscore b. There is, however, a narrow window around T b display style T underscore b, where the measurement time and the relaxation time have comparable magnitude. In this case, a frequency dependence of the susceptibility can be observed. For a randomly oriented sample, the complex susceptibility is chi omega equals chi s p plus I omega tau chi b 1 plus I omega tau. Display style chi omega equals frac chi underscore sp plus I omega tau chi underscore b 1 plus I omega tau, where omega 2 pi display style tfrac omega 2 pi is the frequency of the applied field. Chi s p equals n mu 0 mu 2 3 k b t. Display style chi underscore sp equals tfrac n mu underscore 0 mu caret 2 3 k underscore b t is the susceptibility in the superparamagnetic state. Chi b equals n mu 0 mu 2 3 k v. Display style chi underscore b equals tfrac n mu underscore 0 mu caret 2 3 kilovolts is the susceptibility in the blocked state. Tau equals tau n 2. Display style tau equals tfrac tau underscore n 2 is the relaxation time of the assembly. From this frequency-dependent susceptibility, the time dependence of the magnetization for low fields can be derived. Tau d m d t plus m equals tau chi b d h d t plus chi s p h. Display style tau frac mathroom d m mathroom d t plus m equals tau chi underscore b frac mathroom d h mathroom d t plus chi underscore s p h. Measurements. A superparamagnetic system can be measured with AC susceptibility measurements, where an applied magnetic field varies in time, and the magnetic response of the system is measured. A superparamagnetic system will show a characteristic frequency dependence. When the frequency is much higher than 1 tau n, there will be a different magnetic response than when the frequency is much lower than 1 tau n. Since in the latter case, but not the former, the ferromagnetic clusters will have time to respond to the field by flipping their magnetization. The precise dependence can be calculated from the Néel-Arrhenius equation, assuming that the neighboring clusters behave independently of one another. If clusters interact, their behavior becomes more complicated. It is also possible to perform magneto-optical AC susceptibility measurements with magneto-optically active superparamagnetic materials such as iron oxide nanoparticles in the visible wavelength range. Effect on hard drives. Superparamagnetism sets a limit on the storage density of hard disk drives due to the minimum size of particles that can be used. This limit is known as the superparamagnetic limit. Older hard disk technology uses longitudinal recording. It has an estimated limit of 100 to 200 GBit. Current hard disk technology uses perpendicular recording. As of August 2010, drives with densities of 667 gigabits are available commercially. Perpendicular recording is predicted to allow information densities of up to around 1 TBit, 1024 GBit. Future hard disk technologies currently in development include heat-assisted magnetic recording, HAMR, which use materials that are stable at much smaller sizes. They require heating before the magnetic orientation of a bit can be changed, and bit-patterned recording, BPR. In addition, magnetic recording technologies based on topological distortions of the magnetization, known as skymines, have been proposed. Applications of superparamagnetism. General applications: ferrofluid, tunable viscosity, biomedical applications, imaging, contrast agents in magnetic resonance imaging, MRI, magnetic separation, cell, DNA, protein separation, RNA fishing, treatments, targeted drug delivery, magnetic hypothermia, magnetization. See also: single molecule magnet, iron oxide nanoparticles. Notes. Sources: Superparamagnetism of co-ferrite nanoparticles. PowerPoint presentation on superparamagnetism in PDF.